This tutorial describes the setting up of density functional calculations. The calculations of density functional theory are very much like ab initio calculations generally, and one should refer to the tutorial on performing ab initio calculations prior to this tutorial, because I'm not going to repeat much of the discussion for ab initio here. We have a molecule now with no basis sets. The label says none, so we go to density functional. We choose a basis set, as we always do in ab initio or density functional theory. We choose in this case, let's choose a 321. That shows us the basis set on each of the atoms. As in ab initio, we can have different basis functions on different atoms if we want. Basically, anything you can do in ab initio, you can do in DFT. The only difference really is that you have to choose exchange correlation potential in DFT, which you do not do in ab initio. Otherwise, the options are essentially the same, and we could just go ahead and do a calculation now. But there is a few more options to think about here. The basis set options are basically the same. These options are essentially the same as well. You have the ability to do UHF or RHF, and it's really, you shouldn't say RHF, you should say closed shell DFT or open shell DFT perhaps. This is not Hartree-Fock theory, this is density functional theory, but the parameters of doing such calculations are so identical to ab initio that basically we are using the same nomenclature here. And in some cases, because it was just easier to add DFT and keep all the things that ab initio could do without throwing them necessarily away, some of these options perhaps don't even make any sense. This is doing MP2 on the DFT wave function, which is a little bit suspicious, but it could be thrown away, but it's there by default because the DFT operates just like the ab initio program. So again, there's the SCF convergence on the DFT, the iteration convergence. One can calculate polarizabilities. One can't do configuration interaction. Well, I'm sorry, you can do configuration interaction. And again, configuration interaction on a DFT wave function is a bit suspicious, but rather than throw it out, we've kept all these options which are available in ab initio and are now also available in DFT. Their exploration is open to research in some sense as to what they all mean in the DFT context. With ab initio, they're pretty straightforward, and here they're not quite so straightforward. Anyways, one can do polarizabilities as before, described in some empirical, for example, or CI. There are these same advanced options which are basically the same as in ab initio. The difference in density functional is these two buttons here. In density functional, we have to choose a grid numerical integration of the exchange correlation potential, and we need a grid to do that integration with. There is the standard grid defined by Popel as one example, a relatively simple, relatively small grid and relatively efficient grid as a pretty standard option. Alternatively, one can use Euler-Maclaurin for the radial part and Lebedev for the angular part, or alternatively Gauss-Chebyshev for the radial part and Lebedev again for the angular part. The angular part is generally done with Lebedev throughout the DFT package. And so you have to choose a number of points here. If you choose some random number like 24, it will tell you that that number, well, this is telling me about the 0. The radial number is invalid. I'm getting a message here that doesn't like 0, so I need some number of, say, 50 radial points and 24 angular. it will now tell me that the Lebedev comes in specific values, and I cannot use 24. I must use one of these numbers for Lebedev. So say 38 is standard grid, for example. Let's, for simplicity, use the Popel grid. There is the possibility also of deciding to try and make the calculation a little faster by using a cutoff for density terms that are less than a certain value here. We're not using that at the moment. The big thing in density functional theory is to choose this exchange correlation potential. And we have various combination potentials here, or hybrid potentials. They're sometimes called B3-LIP, B3PW91, and so on. Becky 97, a relatively newer one. If we don't use a combination potential, then we have to choose one from column A and one from column B. That is, we choose an exchange potential and a correlation potential. If we choose Hartree-Fock and none, this will give us exactly the SCF Hartree-Fock result. But in general, we would not choose that. We would choose a specific exchange potential, such as this one from Cambridge University, and one that's comparable to it, for example, that matches. Alternatively, we have the option of sort of picking potentially incompatible ones, although the two are independent, and the correlation potential and exchange potential can be chosen independently here. And so if you choose Becky, for example, this is B-LIP as opposed to B3-LIP. But you could choose Becky with a different correlation potential rather than LIP, which it normally goes with for B-LIP. Anyway, so choosing the exchange correlation potential is required. Choosing a grid is required, and then the basis set, and that basically is everything. And then, like ab initio or semi-empirical, you go and choose a methodology to do a single point calculation, to optimize the geometry, to do molecular dynamics or vibrational analysis, or find a transition state, and so on. So setting up DFT is very much like ab initio, apart from choosing a standard grid like the Popel grid, for example, and then choosing the exchange potential and the correlation potential. So that's basic DFT.